Okay, so today I've been talking about this coming up for a while, and we finally get to jump into it. Circuits with memory. So everything we've done up to now is what we call combinational logic. What we're going to be delving into now is sequential. I mean, things happen in an order instead of all at once. This is obviously really important, right? We can't do very much if we don't remember what we did before. The main building block of this, where we start talking about remembering what's going on, is something called an SR latch. So a latch in general is something that takes a voltage and just latches onto it. It says, this is what I'm going to be until something tells me I'm not, right? So they're not very difficult. In fact, we've talked about all the components that we need to build a latch, and it just takes two signals, set and reset. So the way we do this, the book starts out with another way that's highly impractical and nobody ever would, and then it moves on to what we call the cross-coupled SR latch. So the cross-coupled SR latch, let's say we're doing it with NAND gates. This is fairly common. And we're going to have a set and reset and a Q and Q bar. Now, the trick with this that you'll find out really is that the set and reset on these are active low. So it's really not set and not reset. You could also just flip the outputs and say that if my set or reset, then I have not Q and Q. And those, sorry, I have to think about this really quick. I actually think it's the other way around. I think it's still Q and not Q. It's just they become active low as Q and Q bar. The right way to write this, I haven't really gone over, is those dot low. They're active lows. But the active lows can be flipped into bars so that I end up with not Q dot high and Q dot high. So that should be correct for the set and reset. Now, what does it mean? Well, I can either set the circuit or reset the circuit. I don't want to do both. If I both set and reset, we get into this kind of weird, not really stable position. And really, it's probably fine as long as we don't deassert or drop them low at the same time. But let's look at this circuit. What is this circuit really doing? Well, let's say that they're both 0. Let's say that, so Q and Q bar have to be opposite, right? They can't be the same by definition. So if we start with our output as, well, let's say Q is 0 and Q bar is 1. Let's go ahead and check this. What happens? Does this make sense? So set is 0, reset is 0. And we have the truth table for a NAND gate, right? As so. And this is NAND. So AND would be 0, 0, 0, 1. NAND is 1, 1, 1, 0. So in the case of 0, if set is 0 and Q is 0, Q bar is 1. Great, that's good. That would be bad if it wasn't, right? Reset is 0, Q bar is 1, 1, 0. Output Q is 1. Well, sorry, 1, 0. Well, that's not quite what we want. So where did we go wrong? I always hate these stupid things. Oh, this is for the, sorry, I apologize. I mixed up the two circuits for which one I actually really cared about. So this one, the Q bar and Q naught, is actually the NOR gate circuit. This is why I like doing verifications, make sure I'm not crazy. NOR gate, all right, let's go ahead and write the NOR table and make sure this thing works. So NOR is not OR, right? So an OR gate would be 1, 1, 1. So instead it's 1, 0, 0, 0, right? Okay, now again, we'll start with Q is 0, the two inputs are 0. So set 0, 0 is 1. Great. Now we have Q bar feeding back, which is 1 and 0. So let's call this set and reset here. 1 and 0 is 0. Great, there we go. And now, as long as I don't do anything to that circuit, as long as they hold electricity, those numbers are true. But what happens if we set? We raise to 1. Well, now I go 1, 0 for set and reset. So in the case of Q, well, Q doesn't see set yet, right? Because it has to get the output of not Q. But the output of this gate, because I have a 1, 0, becomes 1, 0, 0. So a transfer from 1 to 0, right? So that puts a 0 down here, a 0 still on the reset because I haven't changed that. And now I'm at 0, 0, which flips this to a 1. So that's what set does, is set makes Q 1. Now this is actually true regardless of what the previous state was, which you could go and prove, but set just says, let's make it 0. Well, what happens if we do the opposite? 0 on set, 1 on reset. Well, we suspect it's going to reset it to 0, right? Well, let's follow through. Reset is 1, so we have a 1, 0 because we have a 0 on the Q bar. 1, 0 means 0. Okay, so we've gone back to 0. That 0 feeds around, and we have 0, 0, and that's our only case for having a 1. That's an SR latch, set, reset. We can change what Q is. Q is what we're setting or resetting. Q bar, it just happens that we can easily access it, right? So this is kind of part of the reason that I keep saying the inverters are nearly free. Well, part of that reason is because when we build something with memory, it's just as easy to have Q and Q bar as it is to just have Q, right? It's just one extra wire. It's almost free. So that's why I mean, that's part of the reason that I say inverters are almost free in circuit costs. It's because they're just kind of there by design. We can also do other designs, right? So the first one that I screwed up is the cross-coupled NAND gate with Q and Q bar, but they are not S and not reset. So they're active low sets and resets is the difference on those ones. And you could go back and prove that the same kind of way to make sure it made sense. Start with an initial value and start setting or resetting. Let's see. So I could ask a question around this of like, A timing diagram is a really common question that I would end up asking and say, given the waveform for the following set and reset, figure out what happens. Well, let's do kind of that here with what happens. So I just said we can't set and reset at the same time. Why? What happens? Well, let's check. Is if I have a 1 here, a 1 here, I'm sitting initial at 1 and 0, let's say. Well, so I have a 1 here and a 0 here. So 0, 1 says that my Q bar should be 0. And then Q, well, resets 1, and that was 1 before at the initial state, right? So we've raised them at the same time, so I'm still in this state. So 1, 1 is also 0. But it doesn't make sense, right? That's a problem to say that they're both 0. Well, it turns out that this isn't awful because this Q and that Q bar are not actually physically tied together. So there's no short circuiting going on. I'm not blowing anything up. It's acceptable. The question is, if I dropped set and reset at exactly the same time, what is that value? Right, because if this set was delayed by 1 microsecond and it was a little slow, then it would be Q would be a 1. And vice versa, if the R was a little slow, it would definitely be a 0. But if it's the same time, we enter a metastable state, meaning we don't know what it is really. And it's kind of like setting a card on its edge, and you only have true or false, and it's going to be one of those two. We just don't know yet. We don't know which one it is. So that's the issue with set and reset coming negative, going low at the same time, is it becomes undefined. Okay. So when we make this, we don't want to draw this circuit all the time because it's problematic. It would be annoying. So much like everything else, we make a schematic symbol for it. It's going to have set, reset, and a, let's see, how are they doing? Q and Q bar. And depending if you're doing, well, the definition of this matters, right? So this is saying active high sets. If I wanted to use this circuit, I would just put bubbles at the input, which means they're active low. It's just saying that I can set by setting it to 0, by making S go to 0, right? Active low circuits, you'll see them fairly often. I don't do a lot within this class, but they are useful because they have this natural detection of if the power goes out, right? Your natural state is 1. If the power goes away, you lose that voltage and it goes away, and you kind of have this natural detection of, oh, there was a problem. So that's why we kind of like the active low situation, is because 1 is the idle. Okay, but it is helpful to let you know that this metastability issue is a real problem, and for that reason, we almost never use a simple SR latch in a hardware description language, so like VHDL or Verilog. We just don't really do it very often. You can write them, right? It would just be a description that would say Q is equal to not S, NAND, not Q, right? But we have this issue too there, is we know, hopefully, and you're gonna run into this more likely as we go along, that if I have some function, well, let's actually just use the example here, where Q is getting assigned to not S, NAND, not Q. But Q is an output, right? And VHDL doesn't like us to put a Q on an output on the right side of an expression. It's going to throw an error and say this isn't allowed, and it's going to be really cryptic sometimes. And so we have to come up with another way of doing this. One way of doing it is to declare it as a buffer instead of an inner and out. You can also declare them as in-outs. Buffers for now are probably easier for you guys to deal with. So let's look at that VHDL for just one quick second, where I could say something like entity SR is port Q underscore L for not Q. I could also do like QB or something, but we'll just do it that. And these are going to be buffer of standard logic. And then we're going to have S and R that are inputs, and they're just inputs, right? They're not doing anything weird or special, so they're fine. And they're also going to be just standard logic. And entity. And then we can go on and say, well, let's make this, oh, I need the architecture, I almost forgot. Architecture begin, and I just say Q is not, and I could do it that way, or I could say not this S and Q. So I'll need to make sure that these are right, because these may be active lows, I suspect, on this one. So, well, we'll just leave it. So Q is that, Q low, sorry, because of the feedback. And then Q low. Something like that. We have an SR latch. So it's writable, and it's not even that hard as long as you use like a buffer or an in-out type. Yeah.
Do buffers, like if we wanted to simulate this, would the buffer basically still act like an out? Or
It would be just fine. It would be driven. What a buffer means is that essentially it's holding on to that value and it is driving that value, but it's also waiting for a new thing to be written over it. So it's somewhere in between. It's just kind of like a holding spot. But there's the issue in simulation, which is actually a good question. So in a real circuit, it's going to do what I described, where it's going to like, you're going to deassert both at the same time, and it's going to wobble and then decide on one. Well, in a simulation, it doesn't have all of the information of the physical world, right? So like in the case of a card, if you were in space where there's no gravity and no gravitational fluctuations and there's no wind, and you set a card on edge, it would stay there forever, right? Well, in a simulation, it would do kind of the same thing, except for it gets worse, because at the fastest speed that it can, it goes, it's a 0, it's a 1, it's a 0, it's a 1, it's a 0, it's a 1, and then your computer locks up and crashes. That's practically what happens. So you want to be careful about set reset latches in simulation, because they will do that to you if you accidentally deassert them at the same time, and it's awful and annoying. So why do we like set or reset latches? Well, memory, but they're actually more useful than that. They go on to do some pretty cool things beyond memory. And one of them, I think we're going to see in that coming lab, so it's important for me to call it out, is something we call debouncing. Now, debouncing is a non-ideal situation that happens in, like, say, a switch. Now, we would like to think that, say we have a light switch, right? And it's either on or off. It's either making contact or not. And we would like to think that there's a metal contact here, and when I throw the switch, it just goes clonk, and now it's closed. What really happens, especially with smaller switches, is they go bunk, right? They bounce. Now, in a light switch, that's not an issue. But if you were saying throwing a switch and you wanted to count the number of times you would flick it on or off, well, I throw it once and it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That's a problem. We don't want that because I threw it one time. I don't want to count 9 times. So this set reset latch comes in handy. So let's say that I have a switch, much like what you guys do, right, with the pull up resistors or pull down, however you want to do it. I'm going to use pull ups here. Make sure I do this right. Okay, so now here's my switch setup. A little bit different. So what we've been dealing with before is what we call single pull, single throw, meaning there's one switch and it goes from one thing or not, right? This is a single pull, double throw, so there's one switch and it's either here or here. There's 2 positions. So now what you'll see is both of these I can connect to ground. Their default state is 1. Their default state is power, which is going to be a problem the way I currently drew this with the pull-ups. So I need to make them active low because their default situation is going to be high. And then my switch, when I throw it, look what happens. So let's say I'm on set, so I'm 1. It has that memory, it's holding on. When I throw it to reset and it bounces, what does it do? It goes reset, reset, reset. So it's 1 and then it goes 0, 0, 0, 0. Well, it doesn't matter, right? Because I'm just reasserting the fact that it's 0. That's not an issue. So there's no issue on the bounce. This is a debouncing circuit. Same thing. If I threw it back up and it hits set, it was 0. It hits set that first time, sets it to 1, bounces off. It's not going to bounce all the way back down to the other way. It's just bouncing up a little bit. So it goes 1, 1, 1, 1, 1, 1, 1. Not an issue. Again. So this is debouncing. All right. But say we don't like set or reset latch. There's another kind. And that other kind is called, well, there's actually multiple kinds, but the next one I'm talking about is a D latch, which really, depending who you talk to, my version is it's a data latch, which is to say that it latches onto whatever a data input is. So instead of just resetting or setting, it's going to latch onto the data. Now, the convenient thing for us is that the D latch really is just a slight modification of the SR latch. It was people like, well, we like this SR latch, but we need more functionality out of it. Reset. Okay. So what this does is sets it up so that set is controlled by both an enable signal and a data signal. And we make sure it's robust by taking the D, the data, and inverting it and putting it into reset. So that by design, we can never have set and reset at the same time. Right, because D is feeding into this. So enable is just turning this into a pass-through. This is creating a gate, is what we call this. And saying that if it's enabled, then I can start setting or resetting. Otherwise, data can flip all around and do whatever it wants. So let's go ahead and actually do an example here for these timing diagrams. This one's a little bit more interesting than the other one. Actually, one second, let me double check. I want to do something first. This one has actually a little bit of an issue that I don't like because of what you have to do, right? So this is really a set not low, so it's inverted. So we could also call that not set, right? Because of this NAND gate inversion. So another way of drawing this one, and I'm just going to erase the early circuits because I like this one better, because that cross coupling that we use is actually really helpful and simplifies the circuit and eliminates that pesky little inverter. And now, this is a little bit easier to deal with. There's no inverter here. Simpler circuit overall. And now we can do a little bit of analysis on that, right? So what's happening here is if the data is 1, coming in at 1, we're guaranteed to not set and reset at the same time by having this feedback into the NAND gate. There is a little bit of a delay there, but it's kind of convenient the way it works out, because then you will never have that switch at exactly the same time, because you have to use this delay path and then this delay path before the set and reset. So it's predictable. It doesn't go into that kind of not quite stable state. So let's say I have a timing diagram. And I'm going to have a data that more or less is going to start high, drop, and then I'm going to have an enable starts low. You can transition in the middle of that guy. Yeah. Then we want to see what happens on Q. And let's assume that Q starts high. So if I don't tell you on an exam or on a homework or something where an output is starting, right? Because it has memory now. You kind of sometimes need to know where it's coming from in order to do anything helpful with it. Then what you can do is you can either assume 1 or 0, or you can write X's until you know, right? You can say, I don't know, I don't know. Okay, here we go. When do we know? Well, what we see is if we have an enable signal, right, and we have a data signal, then we'll get 1, right? That's what we're looking for. So here, up till this point, we're not enabled. nothing happens, right? Because this enable is saying, don't do anything with these AND gates. A way that we can simplify this, if this helps, if you picture it, we have a bubble here and a bubble here. So you can just pretend that these are AND gates and there's no bubbles. Everyone see that? Kind of visual simplification. It's an equivalent circuit. So we know that in order to have a set signal, I need data and enable. So if I started at 1, or another way of saying is I don't know yet until here. Right? At that point in time, now I've enabled it. Now I know what's about to happen. Well, it's low. And then here, data goes high. And then low. And then we turn off enable. Okay. So if we've turned off the enable at this point, and then I'm switching data high there, what happens?
Since our enable isn't on, our value of Q should change.
Correct. It ignores that. In fact, it ignores it all the way until enable's back on. At which point, we can go back high. Okay, that's what a D latch is doing, is we're just building a little bit of extra circuitry in front of the SR latch in order to make a slightly different, better, however you want to say it, latch. And then we get to encompass all of that into one handy little latch drawing that would just look like this. Ta-da, right? Now we have a Q, or a D latch. And you can throw bubbles on these to indicate like it's an active low enable or active low both, right? There's ways to change these circuits to do these. A lot of times we'll stick to this one if I'm doing class, or this one if we're in notes out of the book. Just kind of depends what your favorite building block is. So one way to build this latch in VHDL, right? Because most of what we're doing now, I'm not going to make you hand build circuits with memory, is you would just create a process. So we haven't really talked about processes yet, and my day class kind of got in a little bit of trouble with this because the lab today, or this week's lab, you may want to use them. You don't have to, but you may want to. So a process is something that executes one time, anytime anything in that sensitivity list changes. So in our test benches, we've used processes, but we didn't give it a sensitivity list, so it just changed whenever anything changed. This process, we're going to say we only care if the inputs change, which are D or enable. And then process does not have a semicolon at the end, but it does have a begin keyword here. And then you can say, you can't use if statements outside of process, but we're in a process now, so I can just say if E is equal to 1, then right? So this is just saying, sorry, that was like full on stroke there or something. If enable is 1, if I'm enabled, then put D into Q. That's all. Straightforward. There's none of that weird timing stuff. There's no risk of multiple assertions. It's just straightforward. It will store that value for us. Okay. Now we have a D latch. But the D latch is what we call transparent. What that means is, if this is my enable signal, and I have a data signal, and let's say it's really bad. Let's say it's like a bad connection. You didn't plug it in all the way. And so it comes and it's trying to do something like up and down, and then we drop enable. This is our D. Well, our Q is going to do this, right? It's just going to follow along with whatever the D is doing. It's transparent. We don't necessarily like that for digital circuits because we want to take samples. We want to know at a given time. Or another way of saying that is we like to clock our signals. We like to say at the moment a clock hits, that's the value we care about. And we can build a clocked system with using just 2 D flip-flops. And I'll just finish writing this for a second and then I'll come back to it. Because this gets really interesting. Oh, sorry. All right. So now we have this thing called a clock. And what a clock does by design is it sits and goes, I like this marker's going to give out on me. And it ticks along like so. And then if data comes along, well, let's find out what happens. So what I'm going to have data do So let's think about this. When the clock rises, so when the clock is 1, well, actually, let's start 0. It's a little bit easier. So if the clock is 0, here, whatever data is doing passes right through, right? Because 0 here means 1 at enable. Okay, well, then this means it's sitting and kind of wiggling up and down, doing whatever it wants, until this goes to 1. Then the enable turns off here. But this has been doing nothing at all. So now this enable turns on. So here it's wiggling along, enable goes off, it sticks to whatever it was because it's no longer enabled. And then this enable clicks on and is able to pass that. So this is a 1. Pass that 1 through. So another way of saying that is, remember, okay, so, well, let's continue on for just 1 second. So now if I flow back to 0, well, this turns off, right? And we've kind of talked about it, that there's a little bit of delay here. So this hasn't had a chance to do any of the wiggling that the D would do. So this 1 is now locked to that Q. We're still 1 here, regardless of what this wire is doing, because we're not enabled. Okay. Then if I flow back to 1, I clock it again. What this means is the only time that our final output Q updates a value is on the rising edge of the clock. So that's what you're hearing me say, rising edge or falling edge. This circuit only updates the final output on a rising edge of a clock. Does anyone see why? Does anyone not see why that? Does anyone have any questions? Okay, so let's go ahead and take a peek at, in this event, what does, let's call it Q1, and then I'm just going to call this F to differentiate. Go ahead and take a moment to draw out this timing diagram . Do this. F is, yeah, no, good question, that's fine. Okay. So the first thing that happens is we know that the Q1, which we're calling here, is just going to follow data as long as enable is on, right? So enable is not clock, right? So if clock is low, starts low, we just follow data. But then it's high, so we're locked in, still low. This rising edge is where we actually can first, oh shoot. Clock low, clock low, okay. This rising edge is where we would seal it because we're following here. So we rise on this one because it's transparent on the low. And then we lock in until not clock is the next time that we could possibly change, right? This point, clock is low, data is low, so it does change. We're low until this point, but I did see a raise here before we left. So it rises back up and follows it and then gets locked in until this point. So what I'm kind of doing is I'm going and finding points where we can change, right? The start that I can change. And then just kind of making sure I stay locked until those points are true. So I can now change. Well, it's a 1 here, but then it drops. It continues 0 and gets locked in until this point at which it drops low. It can change. Well, it's low until it raises high and then continues on. Well, that's Q1. Now, F is going to just follow what's happening. On Q1, when clock is 1, right? So clock is 1, we follow 0. And I'm just going to hold on to that for the entire duration of what it was, right? So now clock is 1 again, I can follow Q1. Okay, we're locked until this point. I can now follow here, we're still 1. That was 1, we can follow, it's a 0. Still 0. And then the clock is 1, so we can follow, it goes up to 1. Well, another way of kind of saying that is if you see rising edge here, clocks in a 1. Rising edge here, clocks in a 1. Rising edge here, clocks in a 0. Clocks in a 1. This one clocks in a 0 that I forgot to do. Well, I guess I don't really know here what this is, right? Because I haven't seen a rising edge of a clock yet. So I don't really know. But let's look. So we got a 1 on the rising edge. Rising edge is another 1. Rising edge is a 0. Rising edge is a 1. It works. So I could just skip to the F. I don't even need to worry about Q1. But this is kind of the proof, right, that of why this circuit does what I'm saying it does. It has a clock. So what is the difference then between the DQ flip-flops in this configuration, which I will tell you, traditionally they're called master and slave flip-flops for kind of obvious reasons that terminology is falling out of favor. On this one, I don't know what they're moving to. Well, let's talk in 3610. This kind of master-slave notation is really prolific in industry, and they're doing a pretty active job of moving away from that notation. And in 3610 it comes up more, and we'll talk more about what it's moving towards. I just don't know because we don't do a lot of design with this low-level stuff. But just so you know, you'll see that in industry for decades to come, just because of legacy stuff. So this configuration has taken 2D latches and turned them into 1D flip-flop. Now, the clock is a special signal, right? This is different than what we've dealt with before. So instead of just writing clock, we actually give it a little triangle and then say clock. And in fact, a lot of times you'll just see the little triangle. What that means is that's an edge-triggered signal. It causes a reaction on its edge and only on its edge. Now, you can, as I said, you could have a falling edge clock just as easily. The way you would notate that in the schematic symbol is, surprise, a bubble, right? So if you have a bubble and a little arrow, triangle, sorry, it means it's a negative edge clock or a falling edge clock. And that would update D on the falling edge and only on the falling edge. Okay. So there's a couple different things that you'll see on the kind of add-on pins into this. So one thing that is really useful to add, and I'll do that in red, is RST, or reset. And that's just a way of giving it a signal that says, go back to 0, right? Just like the SR latch, and it's just a way of saying, we need a common place to start from. Because if we don't know where we start, sometimes we don't know what the set or reset. Well, set or reset is obvious. But we're actually going to coming up learn something called a JK flip-flop that is maybe not so obvious. But that's all a reset is doing. And you'll see it notated RST. You'll see it potentially, in fact, very, very often will be active low. Again, the reason is because if it's enabled on, the power is going to be high by default 1. If the power goes away, it drops to 0, and it goes by default to the reset state. And what that means is when it gets turned back on, it's turned back on into a very predictable state. We know what all of the circuits are doing if we use active low resets. It's kind of nice designed that way. All you need to do on the NAND gate SR latch is if you were to look at the bottom, again, you just start from an SR latch actually. And on the bottom one where you have this cross coupling, then you have R for the regular reset, and then you have another additional signal for reset. That's all. It's a really simple modification to do. But we can kind of build on that idea. Is beyond a reset, what if, so here we're using the enable as a clock, right? What if we still want an enable? What if we want to be able to turn this off? So let's start with this is like the simplest way you can draw a DQ flip-flop, right? So the triangle mean that's where the clock plugs in. The D is where data goes in, Q is the output. I'm not going to draw a Q bar, we'll keep it nice and simple. So let's say I want an enable on this device. There is a kind of brute force way of doing it that we've kind of talked about with enables before. Does anybody know how we could add an enable to this with minimal external circuitry? So phrased another way is I only want to clock D onto Q if an enable. So we're going to have data, we're going to have clock, and we're going to have enable. And I only want to clock it in data into Q. So that this is like kind of the terminology you're going to hear me use all the time. Clock data onto Q if enable is true. Yes, exactly. And now this only toggles if enable and clock. However, there's an issue with this design. Anyone figure out what the issue is? Well, it turns out that what happens if enable is a bad signal and it wiggles a bunch? It looks like a clock. This input doesn't know if it's getting the clock from clock or enable. So it can actually dual clock. And in fact, it can be an issue because you can have a very close switching of like the enable coming on and the clock coming on and the enable going off, and it's thinking it's like clocking at twice the speed. And your circuit will look like it's working because it's clocking stuff in at way too fast. You're like, what is going on? So this AND gate actually turns out to be not a great way. So this is a gated clock. And you're going to want to know that term, gated clock, because I'm going to ask an exam question about this, almost certainly. Sometimes I forget, but I'll try. And it's bad because you don't know if both the clock and the enable can function as a clock. Okay, so how do we fix this design? Well, it turns out that I've been hammering this idea of muxes into you guys this whole time for a reason. Let's see. Sorry, just trying to decide if I wanted active low or active high enable. All right, Kaylee, is that an active high or active low enable?
Active high.
All right, let's think about it. If you're 0, then you select this, and your next data, the next time a clock happens, it stays Q. Whereas if enable is 1, the next time a clock happens, data gets passed through. You are correct. It is active high. Because when enable is true, we'll take data. If enable is false, we'll just take the old Q. Does that make sense to everyone? So this is a good way of doing that. So that we're not gating this clock. We don't have to do anything weird with the clock. But we still get to choose whether just to hold the same data or move on to the next. And there's no opportunity for this enable to really mess anything up. It can go up and down all at once, more or less. Okay. There's something else that we can do to these circuits that you'll see fairly often. Which we call output enable. And what this does, so this is just a picture of a buffer, right? It's like an inverter. But all it does is, depending on whether the output is enabled or not, it drives the signal or not. You're going to end up using this in project 3 actually down the line, so I want you to know it exists. We don't need much with it yet, but it's just a way of saying sometimes I want it to drive a line, sometimes I don't. So one example of that is, let's say I have 2 DQ flip-flops. And sometimes I wanted to drive it from, we'll call this memory 0 and this time memory 1. If this guy also has an output enable, but we just invert it. Oh, not an inverter, sorry, just a buffer. These can actually both attach directly to the same wire without the need for a mux. So it's a little bit simpler because buffers are a little bit simpler than a mux. And they can both share an output wire because only one of them will be driving it at a time. So that's one purpose of output enables. Similarly for this, you'll sometimes see it as a circuit schematic that has like this. So it has a data, it has a clock, and it also has output enable. That's what OE is. You could also see it with just E, which is this enable. You might also see it like that with both an output enable and an input enable, right? And that each of those options makes more and more complicated circuits to build. But it's just a couple extra inputs on gate, so a couple extra transistors. It doesn't cost a lot to do, and it adds quite a bit of functionality. All right, next one. And we'll come back. I'll do some more timing examples, I believe, because I think, yeah, kind of going through this fast. All right. So you've seen me. I don't do it often yet, where I'll write a slash through a signal and say 8. What this means is this wire is a bus. A bus is really just multiple wires in parallel. And it means that there are 8 bits inside of this guy. All right, then, if there are 8 outputs, I need 8 inputs, I need 8 outputs. Go ahead and throw a clock on here. What does this mean? Well, really what this means is I've taken 8 of these, maybe not with the OE, right? I don't have an output enable, so there's no E's. And instead of being connected together, they're in parallel. So there are 8 D flip-flops. So remember, latch is not clocked, flip-flop is clocked. SR latch is set, reset. D is data. So this is 8 data flip-flops. So 8 clocked memory devices in parallel. What we call that is a register. You're going to hear this term a lot. This is like the basic fundamental building block of all what we would call cache memory. These registers are part of what defines processors. So if you went and got like an ARM processor, right? ARM is just one form of architecture. It's going to be 8-bit or 32-bit or 64-bit. What that means is how many bits, how many D flip-flops does it have in its registers? When it tries to access its memory, how many bits does it pull in at a time? That's what the register is telling you. Now, using these things is really easy. It has memory, so it needs to process, right? It's sequential logic instead of combinational. And you could do something like if enable, then and what's nice is when I declare, oh, forgot one part of this process, the sensitivity list. Now, but there's an issue here, actually. We haven't talked enough about process sensitivity lists. I've said enough words, but I haven't highlighted it yet. Does anyone think what the issue with this process might be as is? When does a process execute?
Every rising edge of the clock.
Not quite. When does a process execute?
When something in the sensitivity list changes.
Exactly, when something in the sensitivity list changes. So what happens is this rising edge or falling edge? Both. Why not both, right? We don't have that definition of, ooh, well, it's going to execute every time it changes, which the VHDL is not going to like very much, to be perfectly honest. So they give us this nice tool. Sorry, I'm going to make sure I write this absolutely correctly because sometimes I screw this up on the first time. If rising edge of clock, then. All right, so what happens now is every time the clock changes, this runs. But if and only if it's rising edge, will it actually execute what's inside this if statement?
Should we add an and enable as well, just so that way we wanted to say?
Yes, you can. And in fact, what you'll start to see fairly often is embedded if statements. And in fact, a really important one, let's say we want a reset. So like the enable, but the reset is the most important thing, right? If the reset is happening, I don't care about anything else. So the easiest way of doing this is probably inserting it above. So process, clock, begin. And then, actually I should have left that. Well, here we go. If All right, that's kind of squished in there. I'm gonna else if. All right, if reset is equal to 0, then else if rising edge of clock, then. In the back, is this a active high or active low reset? Active low, because if reset is 0, then we're gonna do something other than assign Q, right? And an example of this is, let's say it's 8 bits. Well, that was annoying to write, right? Well, there's an easier way that we can do that. What does the X mean?
Hex.
Hex. This is saying that what comes after it is hex. That way, right, this is 8 bits in hex. There we go. This is a nice active low reset D flip-flop. Sorry, D flip-flop based register, right? Because there's 8 bits in Q. I will point out, in case it's not obvious, you can also write falling edge if you'd like. There. So this is what we call a synchronous reset, kind of, because you can only reset on this if clock changes. And in fact, you can make it fully synchronous if you want to put if inside of the rising edge. You could say, I'm going to really shorthand this, process on clock if rising edge, you're going to see this abbreviation a lot, RE, I don't want to write out the correct command, if RE clock, I may even leave out clock in this one, right? I could say if rising edge, then if reset is equal to 0, then else if, then else Q is D. So this is a fully synchronous reset, meaning I have to have a rising edge of a clock and 0, and 0 on the reset at the same time. Alternatively, if I want an asynchronous reset, which means that the reset happens no matter what, no matter when. This is almost there, right? Because this will activate on either the positive or falling edge. What do I have to do in order to make this code into a fully asynchronous reset? No idea? It's okay.
We could add a reset to the sensitivity list.
Exactly. Now that will execute if either clock or reset occurs. And then the first thing that gets evaluated is reset 0. So if reset changes and it was 1 and now it's 0, it won't evaluate Q in any other way other than to set it to 0. So that's asynchronous reset. The other way that I kind of sketched out is a synchronous reset. Generally in this class, I will ask you to do this one. Don't forget the reset here because that will cause you grief. Don't put anything else in the sensitivity list because that will cause you grief. If you ended up with like your input D on the sensitivity list, I have seen this before in labs and it's not great. So you have this clock, right? And you'd ideally have clock plugged into there that's rising edge. Kind of what you do if you add that, this isn't quite fully accurate, but if I were to add D to the sensitivity list, I kind of have done this, which is just nonsense, really. It would cause you timing issues all over the place. So be aware when we're doing sequential circuits in this class, we almost always want to do synchronous circuits with the exception of the reset being asynchronous. Okay. Other rule that I have in my notes just to highlight, anytime you're inside of a process, limit yourself to one and only one rising or falling edge statement. If you need it, you can actually have multiple processes in one VHDL file. That's fine, but don't put multiple rising edge inside of the same process. That will cause you really difficult to track down errors. If I wanted to add an enable, where's a good spot to do it? Because you brought it up.
Maybe, yeah, so we'd want to add the and to the rising edge of the clock.
Yes, so you could add if rising edge of clock and enable. An easier way to do it, if you want, it's kind of up to how you guys prefer. I don't really do in VHDL a lot of this and that, especially with the rising edges, because it makes the debugging more difficult because the errors get kind of unclear. So for this purpose, I do kind of recommend doing an embedded if statement. It's the same thing. It simulates the same circuit. But what this does is, this is a new row. And if I did something weird with the enable in an external circuit and I get an error, then I get this whole row with it that says error, we don't know what happened. Whereas if I get the error here, it'll say something error enable is undefined. It's just more debugging friendly, which for beginning programmers is kind of useful. It's not wrong. Okay. I'm going to introduce this now as a simple, let me double check that I'm doing okay on time. Oh yeah. You can add the output enable, but it's a little bit tricky and you're going to want to pay attention because you are going to do this in a lab later. We'll circle back around to it and talk about it again. But as I said before, I like to give kind of sneak peeks so that when we see these new harder materials, it feels like, oh yeah, we've seen this, right? So process clock, I'm going to say if reset, I'll keep the synchronous, the asynchronous reset. And then I'm going to do something a little bit confusing. So outside, before this process, inside of the architecture, I'm going to create a new signal that is just simply called, I'm going to call it IQ just to be funny, internal Q. So I'm going to use this inside of the Q block only. And it's going to be a standard logic vector, blah, 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 right, of the right size. So I have this IQ. And what I'm going to do is say, if I have a rising edge of clock, I'm going to get rid of the enable that way. And I'm going to say, so I'm going to make an output enable instead of the input enable. And what I'm going to say is IQ gets assigned to D. And then outside of the process, I'm just going to say that Q, so like the actual output, not internal Q, but the actual output, and I'm going to reassign the reset to IQ as well, is going to equal the internal Q when output enable is equal to 1. So if I'm output enabled, then Q gets that. Otherwise, so else, Z. And I have to have 8 Z's because it's 8 bits. Now notice, this statement is okay to be outside of a process. The ifs have to be inside, this can be outside. What this is doing is creating that buffer that is just saying, if I'm not enabled, we're just going to kind of disconnect there and break it, and it can do whatever it wants. We're not going to drive our value onto it. So that's how we make an output enable.
And on that one, would we also have to include our OE inside the ports?
Yes, you would need an OE in the port. Yeah, sorry, I haven't done any like the entity declaration or any of this. So yeah, anytime you have a signal like this that's like a condition is what we call this, you need it. And there's a trap that people fall into. We do need this whole thing that says when OE equals 0 because we're standard logic. Because standard logic can be 0, 1, Z, H, L, right? It can be lots of different values that we haven't really gone into depth. If we were dealing with just strictly bit types, then you could just literally, if OE was a bit type, you could do when OE. Because a bit is strictly 0 or 1. But I always assume that you're using standard logic, so you need that comparison. Just so you know, people, especially like that have experience in C, try and do that all the time. They just say when OE else, because they're used to the strict bit type. That standard logic just isn't that. Okay, let's talk a little bit about the applications here, some of the other stuff we can do with the flip-flops, right? So we started off with the SR latch, we made it into a D latch, turned that into the master-slave relationship between the two D latches, and ended up with the D flip-flop. What can we do with the D flip-flop? Well, we have this idea of clock dividers. So I drew the clock for you, right? The clock is just this thing that goes up and down at 0 or 1. This is a digital clock, right? This is what all digital logic recognizes as time. This is why I can't say wait for 10 nanoseconds, because it's not counting time, it's counting clock edges and just marching along. Well, if I want to change that clock time, right? So we make a clock on like an FPGA, like what we're going to deal with later in this class, and a lot in 3610, using a crystal oscillator. So we literally use a crystal, and it generates a fixed frequency for us. So frequency is just a description of how often the clock happens. Now, frequency is an F, is related to the amount of time between two rising edges in an inverse manner. So the frequency is just 1 divided by t, the period. That's what t is, capital T, period. So the amount of time that it takes in between rising clock edges is the period. How often that happens is the frequency. So a period is measured in seconds, and frequency is per second. So your clock might be something like 100 megahertz. Okay, hertz. Well, hertz is really just once per second. Its unit, scientific unit, just like meters, right, is per second. So this means 100 million per second. Okay? That's all frequency and period R. You're going to hear me use it a lot. I'm going to probably ask you a question that's going to be really simple, like, what's the frequency of the following signal? And it'll have a plot and say T is equal to 60 milliseconds or something like that. Right? And then you just do 1 divided by 60 milliseconds, and boom, there's your frequency. Okay. Well, we have a clock, we have a crystal. We don't want to put 1,000 crystals on it in case we want any variation of frequencies. What if I have a 100 megahertz clock and I want a 20 megahertz clock out of it? Well, we call that clock division. Not exactly a fancy word, but useful vocabulary. Sorry, I'm just making sure I don't miss anything before I jump into this next bit one. You can do some kind of interesting things with it. So let's go ahead and have this D flip-flop. And it's going to be clocked at some rate, right? And we want to have this Q output be a new clock. Well, it turns out a really easy way to do that with clocks is just take not clock, right? Because that's all a clock doing is after every amount of time, we say clock is not clock, just up and down, up and down, up and down. Cool. So that's what this is doing, is every time a clock edge hits, the new clock, Q, becomes Q bar. Okay, so what does this look like? Well, this is clock. And Q starts at 0. So clock, Q. So D, meaning rising edge of clock, Q is going to take D, which is just not Q. So if Q starts at 0, rising edge of clock happens, it switches. Nothing happens until the next rising edge of the clock. It just switches. We just divided by 2. So it turns out clock division by 2, or multiples of 2, is trivial, right? Because if I just did that and attached this new Q, I'm now divided by 4. Okay. Anyways, that's clock division. You can end up with like clock multiplication, but those that was PhD level coursework for me. So I'll save that, guys, for you for 3610. Okay. We're going to introduce a new one, a fun one, a useful one. It almost always ends up on the test, and it's called a JK flip-flop. Now, the JK flip-flop is a little bit weird, and we're going to go back to our old friend, the truth table. And it's going to, you're going to introduce some new notation here. And I actually should check. Sorry, this is the notation that I learned with. I need to go back and make sure that the book is doing it. I'm using a little bit different notes, but the book covers the same general ideas. Where it's Qn plus 1. What that means is the next clock is, rather than what's now, what is the next thing that happens based on our inputs, J and K. Well, its truth table is as follows. All right, so what that's saying is, if I have JK as both 0, the next clock period is the same as it was last time. Don't do anything. K then is functioning as a reset, right? If it's just K, we reset to 0. J functions as set, go to 1. J and K together, not Q. Inverted, flip it, flip-flop, right? That's the JK flip-flop. Very important, very useful. You can actually build really easily an SR flip-flop. Where, once again, 0, 0 is don't do anything. 0, 1 is reset to 0. 1, 0 is set to 1. And 1, 1, just like the SR latch, in the SR flip-flop, it is don't do that. But what's nice is you'll notice that the JK flip-flop and the SR flip-flop are the same, with the exception of this one. So you can actually use an JK flip-flop as an SR by just not ever doing this. Okay. Now, this is where normally, there's this tool called variable entered maps that I've alluded to before, or map entered variables, one or the other. That just takes this truth table, like it builds the truth table out, and it uses variables similar to the way that we use just zeros or ones. And it's saying that, well, 0, 0 is Qn, 1, 1 is not Q, and then 1, 0, so J 1, 0 is 1, and J is 0, 1 is 0. And you can use that to go ahead and fill in the logic equations. You don't have to do that because you can go in and make like you could just do it in more complicated truth table. It's the same thing as just adding another row of Qn, right? I don't like covering variable entered maps because they're annoying, but I want you to be aware that happens. If you go out and wrote this out, did the whole truth table, and simplified it down, you'd get basically something like, make sure I do this right. right? I mean, it's pretty simple, and you could almost come up with that on your own for when it's 1, but it's just not that important. What's important is that you understand these truth tables for the JK, because the JK is kind of fun. And implementation of the JK that we can get away with is really just start with the D flip-flop. Right, so in that equation, right, where the data input, what we need has this idea of memory, so it's going to use what we call feedback. So we're taking, this is Qn, what's happening right now. This is Qn plus 1. Okay, and then we just take the advantage of not K, J, and not Qn. That's our JK flip-flop. All right. I'm just going to start writing. I'm not going to do the whole JK flip-flop, I don't think. But it is a good opportunity to do what was your name again in the front row? Chris alluded to, which is the and statement for multiple conditions. So where J and K, I shouldn't have erased the table, but right, if J and K is both 0, 0, you can say if J is equal to 0 and K is equal to 1, then Q is equal to 0. I had to go back and look at my truth table. Right, so this is just this condition, multiple conditions. This is saying if J is 0 and K is 1. And then you can do else if, there's an annoying thing with VHDL where when you write the else if, there's no E in there. It is no space else if. I don't know why they decided to do that, but they did. All right, a little bit of an issue here, right? Because I'm doing this kind of internal stuff. What I could do, I could probably juggle away and say there's a signal called, no, I probably have to do a buffer, right? Or an in out on this Q in order to make this one work. I have to think about it for a little while. There's almost certainly a way to do this without a buffer. Let me think for a second, see if I can come up with a quick way of doing it. Yeah, I actually don't know yet. I don't know of a quick way of doing it without just making a buffer or an in out. So be aware of that. Then, so I've got 0, 1, 1, 0, and 1, 1. Do I need to write a statement for 0, 0? Haley? What's the 0, 0 of the JK?
Does it change?
Doesn't change. So do I need to write it? No, I don't. I can just ignore it because I don't need to do anything, so why? All right. The next one is the simplest one of them all. They're kind of cool. They have some really interesting applications in clock division, especially. They're just called T flip-flops. And their truth table is the simplest of all, where T is either 0 or 1, and Qn plus 1, if it's 0, is Qn, and if it's 1, is not Qn. So all T is doing in this case is saying flip or don't flip, just flip-flop. This is like the fundamental flip-flop. Either do it or don't do it. Unsurprisingly, you can very easily build a T flip-flop out of a JK flip-flop. I might actually save that for a homework though, because it's kind of fun and simple. Okay, wow. Should be 6:30, so I'm a little behind schedule, but I think we'll still finish early probably. All right. So let's go ahead and use T flip-flops to build a counter, actually. Let's go the other way, which if you think about it, clock dividers are really just counters that just flip a bit when they're done counting to some number, right? 2 or 4 or whatever. So we know in a counter that we have this, right? And there's this kind of interesting pattern. Because in the first column, it flips every time. And so if you picture this as a counter that's counting clocks, so each time a clock hits, I want to step from one to the next, right? Well, in the first column, every time a clock hits, I want to change. In the second column, I only want to change every 2 times. Another way of saying that is really on the 0, 1, 0, on the falling edge of the first column, toggle the second one. So T for toggle, right? That's all that's saying. Well, let's have a clock enable that turns things on or not. And that clock is going to go in, and it's just going to say, and that. This is T input, by the way, T. And then the output Q goes there. And then the regular old clock goes directly into this guy. Well, let's feed it around to all of them so that all of them have a clock, so that we're running off of the same clock. So we're nice and reliable rather than having like this weird delay path of clocks. We're just going to run off of the same clock. But we're going to take advantage of this clock enable to toggle or not toggle. But in the second one, I don't necessarily want this clock enable because I only want to change based on this guy. So let's take Q as our output and say that if Q has happened, make sure I did this right. Okay, good. So if Q is 1 and this Q is 1, then this T can see a 1. Now I have this nice simple cascade. Wait, sorry, I was skipping ahead to something. Let's not do that one, and it wants to, let's pull from the and situation so that we're just worrying about that bit. We'll simplify it for you guys for a little bit. Okay, so that way, if we're enabled and this is a 1, then this is going to toggle and tell the next one where it's at in the toggling situation. Then this guy still helps us, this Q, because that's still going to be for us what we'll call Q0. And we can pull this one and call that Q1. And lastly, our Q3, or we'll skip one, Q2. And so what this is going to do for us is, let's just assume I'm enabled. I am counting, right? That's all the clock enable is doing for us, is saying that we do want to count. All right, so that means if we start at a 0, then the clock hits here and we toggle Q. So it goes 0, 1, 0, 1, regardless. All right, well, because clock enabled, this is doing 0, 1, 0, 1. But as we showed before with the clock divider, because that's switching here, we're only waiting until every other one kind of ticks along. So it's half as fast. And then the next one is half as fast as the previous one. So as they kind of march through this clock, we're just counting up. One of them is going 0, 1, 0, 1, the other one goes 0, 0, 1, 1. Right, and there's several ways that you could implement this without the clock enable. You could use even D flip-flops to build a counter, really. But you guys, maybe less so in this class. I'm trying to think. No, you'll actually end up using it. So, counters. The reason we want to bring up counters is less about the architecture and more about why we use them. So let me say that I have a 10 kilohertz clock. That means it's happening 10,000 times per second. Take a brief minute and tell me what the period is for that clock. period.
Tenth of a millisecond.
1/10 of a millisecond, 0.01 milliseconds,
Or 0.1.
0.100, right? Or sorry. Okay, never mind, you're right. I'm just dumb. Yep. Okay. So now let's say, as I'm going to in a lab, that you're asked to build a garage door opener using digital circuits. And it wants it's only going to respond to the garage door button if you hold it for 1 second. Right, so it's like, if you accidentally bump it, I'm not going to do anything. If you sit and hold it, I'm going to react. How many clocks do I need to count to get to 1 second? How many clocks do I need to count to get to 1 second? Well, if I do 10, then I'm at 1 millisecond. That's okay. It's really just 10,000, right? Not that tricky. It's just saying, if I need to count this many times to get to 1 second. But a lot of times we're not counting to 1 second, but we want to understand this conversion. So if I'm saying you need to be able to, and this is really important, I will ask on a test, if I give you a clock frequency, I may tell you to convert that. How do I make a clock that counts to for 30 milliseconds, right? Well, I can calculate the period as 1 millisecond, and then I simply need to say, well, if I have the period, I'm looking for a number of clocks, right? A number doesn't have a unit, so we know that there's going to be a division because you're going to do something milliseconds. So what I'm going to do is say, I want 30 milliseconds. How many clocks to get to milliseconds? Well, we can kind of intuit this, right? So it's going to be 10 times 30, so I need 300 is the result. But it's a lot easier to figure out this equation roughly, right? And if I'm doing this, 30 divided by 0.1, what do I get? So there we go. Time to clocks. That's how we do that conversion. It's an important conversion because digital circuits don't know what time is. It is your job to be able to take their language of hertz, clocks, and turn it to actual time. Okay, this next part is fun. I like this part because it's hard. This whole time we've been pretending like circuits are ideal and have no delay. And I keep alluding to the fact that clocks have delay, or circuits have delay. Let's bring it in officially into this class so that I can ask you questions about that on the next exam. But flip-flops have their own timing characteristics. And so we're going to talk about it in really interesting ways. So they have a couple different types of delays. One of them is a timing restriction that we call TSU, or setup time. They also have TH, hold time, and, well, this is how I'll write it. I'll go check on book. Clock to Q. What that means is the amount of time between the rising edge of the clock and when the output cue updates. Okay. Setup time is the amount of time required for data. We're going to do this all in the case of D flip-flops, like this. Super simple, super easy. A clock hits, we take whatever's on D and output it on Q, right? Setup time says that D must be stable. It must be decided what it is for a certain amount of time before the clock rises. If I don't meet setup time, I can't guarantee what Q is going to be. Similarly, hold time, not hold Tim, hold time is what is the amount of time I must stay the same after the rising edge of the clock. Now, the reason for this is device physics. It's really like charging up an input, and it takes some time to do that, and you need to make sure it's had time, and if you don't, it's like, well, instead of being at 1 or 0, it's somewhere in here, and it will latch to one or the other, but you don't really know where, right? So if this is, this is a 1, that's a 0, and I don't meet timing, I don't know where it's going. That's all it's saying. Again, this is another way, if you don't meet setup and hold, of landing yourself in a metastable state, where it's gonna be one or the other eventually, but you don't know when and you don't know what. Okay. I'm trying to figure out how to do this. All right. Over, how does it falls at? I really hate drawing these, but I've had issues with the overhead recently. So rising at exactly the same as this. Okay. So anytime my clock rises, I need to be concerned about what is going on around it, the input. So I have two inputs in this case, both J and K. So let's say that my TSU is 8 nanoseconds, and my T hold is 4 nanoseconds. And then, well, let's do all of that for now at the moment, and just talk about the potential issues. So, what this means is my setup time before clock must be stable for 8 nanoseconds before this clock edge happens. That's 7, right? So what is my Q? Let's go ahead and do Q here. So Q is I don't know, I don't know, I don't know. And let's say my Q clock to Q, what does this example want to be? Yes, I know, propagation delay are 6 nanos. Let's just call it 6 nanoseconds. 6 ns. My clock to Q, C to Q, is 6 nanoseconds. So at first, I don't know. But then this clock happens, and I still don't know for 6 nanoseconds. That's what the clock to Q says, is I don't know until 16 nanoseconds. But because I didn't meet the setup, I still don't know. And I can't know until 6 nanoseconds after this rising edge. Okay, well, are we okay here? Well, 20 nanoseconds earlier, 10 nanoseconds for this guy and even longer for that one. So here, T setup is great, right? We've got 10 nanoseconds, we only needed 8. T hold, well, I don't change until 37 nanoseconds, so I make it. So now I've clocked this in. What is the value? What is Q at 36 nanoseconds? So it's 0, 1. What happens when J and K are 0 and 1? Set to 0. Sure, I don't remember. I don't memorize. So 6 nanoseconds after this rising edge of clock, we go, haha, we're 0. And we know we must be 0 until 6 nanoseconds here. And now we ask the question, is the setup and hold time met? Here, is the setup and hold time met? It's not. We're changing at the exact same time. Well, even if it was a little bit over, it doesn't help because I need to be 4 nanoseconds over. Right, because that's my hold time is 4 nano. So if I don't meet these setup and holds, I'm in trouble. because I don't know what it is. So there's only this really short window that I actually know what it is. I'll be sure to give you guys homework that asks these types of questions because this very similar question will be on the exam. This kind of setup and hold time violation. And you might be bouncing back and forth between I know what it is to I don't know what it is, or it might be you know the whole way, but you need to make sure you understand. Setup time is the amount of time that the inputs, so J and K in a JK flip-flop, T in a T flip-flop, D in a D flip-flop. You need to make sure those are met. Setup, hold. Setup being before, hold being after. Clock to Q is the amount of time that elapses between the clock edge and its output decision. Now, we're going to get even more fun because we're going to end up with some combinational logic, and I'm going to give delays to that logic, and I'm going to give it some feedback for some decisions. And I'm going to ask you, what is the maximum delay that you can have in the combinational logic before you start getting errors? Now, don't worry, that comes in, well, soon, but we're about to get there. So hopefully this makes at least a little bit of sense, and it will make more sense when you do homework, I know, because we're about going to surge on. How's the time doing? Great. Sorry, this is a really information-dense session, I know. That's why I gave you a bit of a reprieve leading up to this one, because this is hard stuff. Look at that. It is time. I thought I was giving you a sneak peek, but turns out it's on the next page. Okay. So let's go ahead and say, oh, this is an awful color. Okay. B flip-flop. Q. It passes around. I have combinational logic. I also have inputs. And I ask the question, essentially, this is the big question. On this clock, how fast can I run this circuit? How fast can I run the clock is another way of saying that, based on the delays of the flip-flop and the combinational circuits. So when I say combinational circuits, I mean it's going to be like a sum of products expression or something, right? And it's going to be like 10 nanosecond delay here and a 13 nanosecond delay here or something, right? And the question is, how fast can I go? Well, we have this nice little expression that says, well, let me just write this down rather than trying to talk. Okay. The period of the clock. Sorry, I should make sure that that's more clearly a capital T. The period of the clock must be greater than or equal to the maximum clock to Q delay That's what this is all saying, is the maximum period of the clock to Q plus the delay of the logic maximum. So you could have, I don't know, say this happens. Something like that. Your maximum delay then is 5 plus 10 plus 13. I don't get to say it's faster because the C has a shorter. I have to deal with the maximum time. What is my worst case? Right? That's the same thing as clock to Q, is what is my maximum delay? I don't get to take like the minimum, because what is my delay between 0 and 0? Well, it's none, right? Because it's already there. So what is my worst case? Because sometimes your delay will be different from 1 to 0 and 0 to 1. Plus the maximum setup time. So, sorry, the book has an S. I like SU because it's more clear, TSU. So what you'll notice here is, if you're very careful, is it doesn't care about the hold time. And that's simply, it just isn't something that's going to come up from you changing the clock. Speeding up the clock isn't going to be an issue for the hold time nearly as fast as it is going to be a problem for the setup time. Okay. So let's go ahead and imagine back to that 3-bit counter I started building, right, with the T flip-flops. And say that the I probably have to draw this, aren't I? And then you have an AND gate, has clock enable, a Q, like so, and it repeats more or less. Let me go back and make sure I doubled 12. Yep. I probably don't care about that guy because he's reacting the slowest. Whereas here, and it's going to say that we want our logic delay of the AND gate to be 7 nanoseconds. Okay, and then we want to have the flip-flop to have clock to Q set at 12 nanoseconds. TSU equal to 6 nanoseconds, and a T hold of nothing. Let's say we don't care. Now the question is, what is the maximum clock frequency for this circuit? Let me make sure I did everything else right. I need to label some signals here, otherwise you guys can get confused on me. So this is Q naught. This is Q1. And then any other signals I need to label? Oh, the T's. T1, T0, T2. Okay, so what we need to calculate here is what we call the propagation delay. So you don't have feedback per se, but we do have the maximum length of delays that we're going to have to deal with, right? And our worst one that we have to worry about, because we don't care about hold times, we don't really care about the T0, is actually the flow from Q0 through this AND gate to T2. Because if this is okay, if this node is fine, everything else is fine, right? As long as this is ready, there's no problem. This one is always ready, right? We'll just assume it's input here. If it's not, we made a mistake out here. That's easy. That is hard. So what are we looking at? Well, we have this time delay of the logic that's going 7 nanoseconds plus 7 nanoseconds. So that is our longest logic delay. And then I said that my clock to Q was 12 nanoseconds, right? Well, that's easy. And then my last one is setup time, 6 nanoseconds. That's all. So this one doesn't have feedback, but it still has this kind of critical path. It all follows the same kind of thing that we need just to make sure that we have set up that last one in time before we start counting. Okay. I want to see real quick if I can make this thing work. Oh, someone unplugged it. That's awesome. Let's see. Let's try it this way. Yay, great. Now, what's a good one? Okay, let's go ahead and take a moment. I think we have time to do this problem. For those that can't read, it says show the output of a D. I don't mean that you can't read because you're literate. I mean because you're far away. And that's great, isn't it? Okay, show the output of a D flip-flop with a synchronous reset to the following stimulus. Assume Q is initially high, so that's what they're showing at the 1. And T setup and T hold time are 0, meaning you don't have to worry about the setup and hold times. Take a moment to do it, and then I'll go back over. Keeping in mind, the reset is low. That .L means active low, right? And this is a D flip-flop. It'll come back online. And I'll try and give you guys diagrams that are clearly labeled when I give it to you on exams, on homework. Just make sure you're careful. Okay, so let's go ahead and look at this, right? This is kind of a weird one because we talked about how the reset is active low and reset is going to reset to 0. So it's going to drop to 0 as a result of this reset. If you missed that, I don't blame you. I don't particularly like this question because it should start 0, because it shouldn't be able to be 1 with the reset. But fine. The next thing that we want to do is we want to identify locations where it could possibly change. It can't change anywhere other than those red marks, right? That's the point of the clock. It also can't change anytime the reset is low. So here, or more specifically, it's going to have to change here because we said, synchronous reset. All right, so it can't even change here. So I guess I'm mistaken because I thought it was asynchronous reset. It doesn't fall low. My apologies. It can, however, fall low here because we're synchronous. Clock hits, is reset, drops low. Nothing changes until the next opportunity. Clock hits, we're not resetting, so we take D. 1. Nothing can happen until the next rising edge of the clock, right? So this is what you want to do. Identify where it could possibly change. If this was an asynchronous reset, then I would go out and I would add this one, right? Because it could change there. But it's a synchronous reset, so it doesn't matter. All right, clock edge, not resetting, data is 0. Next up, clock edge, we are resetting, so we don't care about this 1. Clock edge, not resetting, R1. There we go. How do we do? Anyone get it right? No, what do we miss?
I just got confused by the reset.
The reset. Oh, did you do it opposite? Or what?
Just didn't kind of.
Okay, that's fine. Let's erase that and let's do another one. We've got time. Let me see if I have any better ones or if I'll go back to an easier one. I guess. So this one is a D flip-flop with asynchronous reset and the following stimulus where we don't worry about setup and hold times. Number 4. So this one does not give us an initial cue. We don't know. Reset.low, low reset. So just to help out so we're not clear, we are asynchronous reset, meaning it happens immediately. So we do know that because reset is low, we're 0, and then we want to go and identify all of the spots that it might change. Ready to go. So most of you guys did this. This is really annoying. This is why I didn't use it earlier. Is it's just awful. Did a great job of identifying these rising edges, which is super important. And then we want to add, and it looks like most of you did this as well, look at the resets and see where those might affect. So here we are resetting, and here we're no longer resetting. So some of you identified this as a spot. It's not going to change there because it's not a rising edge, and we're not going into reset. So it's not going to change what it was before. So this one is don't change. That was the biggest mistake that I saw when I just went around. Whereas here, when this drops, we are transitioning into a reset. So if we were a 1, this would become a 0. Whereas here, whether I'm a 1 or not, 1 or 0, I'm going to stay 1 or 0 in the same spot. So that was the only kind of gap. All right, so here, clock edge, we are resetting, stay as 0. Now we have a new clock edge. We see D, we're not resetting. And in fact, we can go ahead and jump all the way to here. In fact, we're still not resetting. So in fact, all of these are not being reset. We're good. It's just that we're going to end up at a 0. Sorry. Here. Okay. Other than that, data is 1. Data is 0. Oh, this is like really hard for me. Okay, data is 1. Clock edge, data is, well, it looks like data changes just before the clock, and it is still 1, and then resets and drops to 0. If you messed up that last one, I don't blame you. It's kind of hard to see with my dashed lines. With that exception, who got this one right? Only 1? Where do we mess up?
I'm just really confused about why we're not counting where the reset doesn't.
Oh,
like
this?
Explain that one more time. Sorry.
Yes. So at this location,
Okay.
if I am resetting, I have to be 0 for that whole location. So I've reset it to 0. But I can't give it a new value until I clock edge. So the only way it gets a new value other than 0 is with a rising clock edge. So here I'm just no longer resetting at this point. Any other mistakes that we ran into? Everyone, that same one for everyone? You? Made a mistake?
Yeah, I just got confused by the reset.
By the reset again?
Just, so if the reset is 1 when you're checking the rising edge, it doesn't matter?
No, if it's 0, if the reset, because it's active low, so that's what I pointed out. So if the reset is 0, no matter what, data is 0. If it is 1, then at the rising edge of clock, it's whatever data is. So it's just that reset overrides everything else. It says go to 0. Just like a set overrides everything else except for reset that says go to 1. Kaylee?
So it's like it's 0, but then even if it is 1, it has to be updated still.
Yes, exactly. So the first update is this rising edge of clock, because this update, reset is true. So it doesn't matter that data is 1, because of our code that says if reset is 0, D is 0. Q is 0. Otherwise, on rising edge of clock, update it, right? We don't have logic. We don't write logic that says if rising edge of reset, right? We never did that in those examples. So we don't care that that happened. It's just now that we're no longer resetting, we can respond to that rising edge. Okay. Let me look and see if I have, well, first off, time is okay. Sorry, I don't have any others prepped that have a reset on them. Let me see if I can come up with one. Actually, I guess here, I'll do it this way. So let's have you guys do this example first. So this one's a little bit easier. So this one says, this is an SR latch. And show how it responds to the following stimulus. So reset is active low, set is active low. Don't worry about not Q, just do Q. Keeping in mind what happens when you've activated both set and reset. And I'll try and find a better example. This would probably work.
Okay. So let's do this one. So if I have reset is active low, that means when it's 1, I don't care. But set is active low. So what does set mean in an SR latch? A 1. Yeah. And then it goes high. We don't care, right? So really what I'm going to do here is I'm going to identify the spots that are of interest. What's interesting? When is it interesting here since we don't have a clock? Yes. So we look at the transitions to active low is really what we're kind of interested in. Okay, so here we've set, and now here I'm resetting to 0, but then here I'm doing both. I'm setting and resetting. So the issue here is it says, note that Q bar will not be the same as Q when set and reset. So we have to go, ooh, all right, what does that mean? We go back to that thing. What is Q when both set and reset? Yeah.
It should just be determinate, right?
Well, it depends. So that's what I was kind of getting at earlier. That's why there's this trick. And we had, let me just switch. Oh, that's gonna be really hard. Anyways, we end up with Q here, and we have set here. And so if we had Q is Q bar. So Q was 0. So Q bar was 1. So 1 feeds around into this. We get 1 NAND 1, which is 0. So Q is getting set to 0, which means it goes back around and puts a 0 here. And I have 0 reset 0 is also 1. Or sorry, is 0, 0. Sorry, did I get lost? You're 1, you get fed around. 0, 1 is what in NAND? 1. 1 and reset is 0 is also 1. So they're both 1. So they're actually, it is actually known in this circuit. It's just we're not supposed to do it because it can lead to problems when they deassert later. I'm not going to fault you if you went indeterminate for this length. But here, we've now lost, so I actually did miss this one, this interesting spot, where I'm no longer resetting, but I am still setting, so it's still 1. The Q high, the Q bar would change at this point, but it's not. We didn't do that. And now this doesn't affect anything because they're already both high. And then we drop low, which means reset. Goes back high, we don't care. Drop low, reset. Well, that stays the same. Drop low is set. There we go. So if you did this, either way is perfectly acceptable. Did anyone get that one right? for either version. Close. What'd you miss, Kaylee?
I just wasn't sure, like those two, or the X ones.
This?
Mhm.
Well, that's fine. That's okay. If that's all you weren't sure on, it's okay. Because that's a weird situation. I said, don't do that, but you can figure out what it is. But if you did, you're fine. Okay, I think I have time to squeak in one more example, if this works. Come on, where's my mouse? Awesome. I don't know how good this example is going to work out. I just found some random exam question. Okay, so let's assume they're all active high on this one. We have clock, D, enable. Maybe. Extra maybe. Probably not. What? Oh my gosh. All right. So the issues that we may run into here are the overhead projector is awful. Is it my voice? Is it like, am I speaking too loud? I don't. Unbelievable. So the issues you could have here is a setup and hold times, right? Is if there is setup and hold times in this question, which they didn't actually explicitly declare in this question. I think there was probably more that the person that tried to cheat on Chegg didn't submit and then got all the wrong answers. Don't cheat on Chegg. It looks really dumb when you do it because it's like super obvious. I guess we can try and do this one, assume that there is no setup and hold. The angles on this are just trying to illustrate that they're not perfect signals. So just pretend that they're vertical. If you guys can even see it long enough to do this. So it's like this. And do Q. If you can.
It's a good practice for the timed exam.
What?
It's a good practice for the timed exam.
Yeah, there you go. I gotta do this. Ready? Go. I remembered it being bad. I didn't remember it being this bad. I'll fix that in a second. It's a game. See if I can get this done before class ends. There we go. I did it. And now I'll just turn this stupid thing off. Ready, off. Nope, even that's too much to ask. We have about another minute, so we can finish this before class officially ends. And if someone actually on this one is feeling really not confident and wants to go up and do it on the board for the extra practice, I can take a volunteer. All right, I'll do it. I don't mind embarrassing myself. It's just good practice to do it so we can see your thought process, but I know it's hard. Okay. So I said they're active high. They're all active high. So that means that we are just not enabled. We're not doing anything. And what that means is if we don't know Q, what is it? Well, I said you could make an assumption or draw X's. So fortunately for you, as long as you did something up until this point, you are correct. Right? So more or less, we just don't know what's happening up till here. It could be something. I could say it started at 1 or something. This clock just doesn't matter. The next clock that matters is here, here, and here. Oh shoot, I didn't specify synchronous or asynchronous reset, did I? Who here did asynchronous? Who did synchronous? Who doesn't know what they did?
I was just trying to figure it out, like.
Okay, sorry. Yeah, all right. Well, let's go ahead and do synchronous because that's looking like more people did, which means that we only care about it when the clock enable hits. So the fact that the enable goes positive, clock doesn't hit until here. When we hit, the reset is true. So we actually know at this point in time, we're 0. Right? The next time that anything can change, because I don't have to worry about if I'm doing a synchronous reset, is the clock edge. Well, I'm no longer resetting, which is good. I am enabled. My D is 1, so we go 1. Same idea, reset, not resetting, enabled. Uh-oh, what happens if I'm directly on the line? No, maybe I'm enabled, maybe I'm not. right? Well, let's continue on. D is 1. So actually, it turns out it's 1. Why?
Because either enable isn't on to write in a new value for D, or it is and D is already on. So
Exactly. Yeah, so either it's not enabled and it can't change, or it is enabled and we clocked in a 1, so it didn't change. So I'll give you guys homework questions, you work on it. I suspect nothing's gonna be due till after spring break, because that's next week. Hooray. I did post an assignment on Canvas that is really gonna push some of your VHDL practice. Get that done, and I'll see you guys for lab this week. It's a good one. It'll bring kind of everything together, and by the time you figure it out, you'll start feeling like you know how to do things in VHDL, or you're gonna start thinking about dropping out of the major, which I really hope is not the case. It's not that bad, I promise. Yeah. It's fun. It gets really interesting when you start being able to like do things. And you can start building like the heart of the microprocessor. Project number 1, it's pretty fun.
Project for drop out of this science.
Don't do it. We pay better in EE. And it's going up every year.
I'm actually going into CE, not EE.
Oh, that's fine.
It's just one of the required courses, but it's kind of fun.